In problem 3, we're going to go ahead and take a look at a different type of zero for our functions. So before we look at this problem, we really need to kind of develop the definition, a very non-mathematical way of looking at the definition of what we call the fundamental theorem of algebra. Yeah, my handwriting's a little messy today. Fundamental theorem of algebra. We're just going to go ahead and abbreviate this as the F.T.A. On the 4th page of these notes, there is a nice little highlighted section for you I put right there that kind of gives you a very brief definition. And it's stating that every polynomial has the same number of zeros as its degree. So in very simple terms, the fundamental theorem of algebra basically says that a polynomial of degree n, so if your degree n basically means you have n zeros. So if you are a degree 3, so if you are degree 3, 3 zeros. I should see 3 unique zeros. If you are degree 5, you should have 5 zeros. Degree 6, 6 zeros, on and on and on. And we saw that in the very first problem. We saw that. Degree 3, 3 zeros. Degree 2, 2 zeros. Degree 4, 4 zeros. Then we kind of saw what happens with multiplicity. And we realized that we actually have to count the multiplicity into our degree. So even though there's 2 zeros, this ended up being a degree 3 polynomial because one of my zeros was counting twice. Same thing for this one. Even though there's 3 of them, there's a multiplicity of 2 happening here, there's a multiplicity of 3 happening here, so I have to count that 3 times. I got to count that guy 2 times. So this actually ended up being a degree 6. Now we're going to start looking at a different type of zero. So in this problem, they start off with this function g of x is equal to x squared plus 4. Now if I go to my fundamental theorem of algebra, this is a degree 2 is equal to 2. I should see there should be 2 zeros for me. Or I could have 1 0 and just have a multiplicity of 2 happening there. You know, I could have a 0 at negative 3 and kind of bounce along there. But if you'll notice, there are absolutely no zeros slash x intercepts happening in this polynomial. So it kind of starts to beg the question, well, is this fundamental theorem of algebra even true then, if this is not happening for this polynomial? So on 1, it's actually going to start looking at the algebra of getting a 0. So Sam expected this graph to have 2 zeros because it's a degree 2. But then he decided to try to find the zeros algebraically. So he took the function, he set it equal to 0. You know, he moved the plus 4 over to the other side by minusing 4, and then he's got to solve this. So what number squared equals negative 4? And we've talked about this in class. There is no real number. There's no real number that works. So because there's no real number that works, you don't see any real zeros. There are no real zeros. Because I don't have a number that works in here. Instead, in order for this to work, our zeros are no longer real numbers, but they're now have an imaginary component to them, which we call a complex number. So we're going to kind of look at that again in example number 2. Here's another polynomial m of x. It has been factored as much as it can. So here's our m of x. We're going to look at this factor and we're going to predict the zeros of this polynomial. We're going to do it by using technology to check our predictions. So if we look at m of x, we have a x minus 1, x plus 3, and then we have this x squared plus 5. I definitely know I have a 0 at 1, because 1 minus 1 is equal to 0. I've got a 0 at negative 3, but I don't have a 0 here. I don't have a real 0 here, because what do I square and then add it to 5? The only thing that adds to 5 to give me 0 is negative 5. And there's no way I can square a number and get negative 5. This is not a real number. And you'll notice when we put it into Desmos just to check our answer, you're not going to see more than 2 zeros. You're only going to see a 0 at 1, a 0 at negative 3, and you're not going to see any more zeros, despite the fact that this should have more than 2 zeros. So let's plug it into Desmos just to check our work. We're going to go over to Chrome, bring up Desmos. And x minus 1, x minus 1, and x plus 3. That was messy. X plus 3, and then x to the second plus 5. And there's our polynomial. I'm just going to kind of, scoot out of there. There's our 2 zeros that we actually found before, right? We've got a 0 at, we got a 0, I did plug this in. Sorry guys, get rid of that. There we go, that's a little bit better. Let's scoot. What a funny looking graph right here. It kind of like curves on something kind of funky here. Let's double check though. We've got a negative 3, 0, and we've got a 1, 0. But that's it. It's not quite a quadratic because it's got that really weird curve going in there. Let's go ahead and look at its degree of the polynomial. So remember, to figure out the degree, we're just going to go ahead and multiply the first term in each of these. So our degree for this is x times x times x squared. So our degree is equal x to the 5th. So according to the fundamental theorem, I should have 5 zeros going on here. Oh, I'm sorry, it's not x to the 5th, it's x to the 4th. Silly. X to the 4th, I should have 4 zeros. Well, I definitely have 2 of them I know of. I've got a real 0 at 1, 0. I've got another real 0 at 3, 0. But there's 2 more missing because the fundamental theorem tells me that I have 4 of them. But we know that there's no real possible answer to that third factor. So what we do is, in this case, we say there are 2 real zeros and there are 2 complex zeros. And the reason why there are 2 complex zeros is because there's imaginary numbers. The only answer to this expression, x squared plus 5, the only thing that will make that 0 is an imaginary number. So its imaginary numbers are into a number system that we haven't really quite talked about, which is the complex number system. So that's why we call this 2 real zeros and 2 complex zeros. So if you come back over here, I should have 2 zeros to this g of x. What I have is I have 0 real zeros, kind of sounds funny, and I've got 2 complex zeros. So our fundamental theorem still works. It's just now we have to start talking about the fact that there could be some real zeros, ones that we see, and some non-real zeros or complex zeros. Those are the ones that we don't see because they don't have a real number to them anymore. Please make sure you guys read this last little page in your notes because it really does give a good summary of the fact that you can have real zeros and complex zeros.